Welcome, everyone. My name is Jeff Bryan of the Volpe Center, part of U.S. Department of Transportation. I'm your host of this webinar. I'd like to introduce Dick Cogswell, engineer with the FRA for many years. Dick will be our main presenter.
Greetings, folks.
I'd also like to introduce Jared Fidzikowski of the Volpe Center, who will co-present with us.
Hello.
So, Dick, we call this series Railroad 101, a conversation on fundamentals. Could you elaborate?
Certainly. People who are undertaking railroad projects need a basic understanding of these topics: train types, track configuration, basic operations, signal systems. The series of webinars we hope will help project sponsors to better analyze, plan, and implement new services.
Let's get started with this session. First, we'll discuss train performance factors.
Train performance is a function of many factors, those listed on the slide and others. We will talk about train weight, train movements, range in miles, speeds, braking distances, etc.
Dick, aren't these factors important design criteria when planning new services?
Absolutely. In fact, to illustrate the relationship among the criteria, let's go to the next slide. As an order of magnitude, both a 60-mile-an-hour freight train and a 110-mile-an-hour passenger train can take about 2 miles to stop on level track.
Okay, so one has more weight, one has more speed, but they both require about the same distance to stop.
Yes, because of this stopping distances, signals are typically 2 miles apart, and passing tracks are about 2 miles long.
So let's start with train types. This is a list of the train types to be described in this webinar. Jared, could you give us an overview?
Sure. Okay, we have these freight train types. Local freights have the lowest priority, but consume massive amounts of time on the main line. Tonnage trains can carry the most weight. Because of this, braking can be the most difficult of any train type. Manifest trains are the most varied in cargo and weight, and therefore braking distance. Intermodal trains carry lighter weight, high-value cargo, and travel the longest distances. They adhere to tight schedules. And we have these passenger train types. Commuter trains' average speed is low because they make frequent passenger station stops. This includes local commuter and zone express commuter. Intercity passenger rail trains, by definition, connect 2 or more large metropolitan areas. This includes long-haul, short-haul, higher speed, and high-speed trains.
Before we go to the train types, to give our audience a sense of the whole, let's address their relative priorities on the railroad. Dick, how are the priorities set?
Well, the priorities as shown on the slide are generally set by 4 factors: train speed, in other words, how fast the train is going; time sensitivity of the train. Passenger trains are typically more time sensitive than freight trains. Then we have the 12-hour limit for the on-duty crew time. There are contracts for performance. Intermodal shippers pay the railroads large sums for on-time transport of their high-value cargo. There are some exceptions to this, and Jared will mention one.
If a heavy freight train is climbing up a grade, it may be allowed to continue ahead because to stop and start back up would require so much power. A passenger train may have to crawl behind.
Okay, so we're going to go through all the train types, but we're going to do it in reverse priority order, starting with the local freights.
Also called local switchers, local freights carry material from local industries that either originate or terminate freight shipments on a line.
For example, local freights may carry newsprint to paper terminals, propane gas to local distribution centers, lumber from lumber yards, scrap metal back to steel mills, and in the Midwest, grain and covered hoppers.
Local freights are typically slow. Their overall average speed is in the range of 5 to 10 miles an hour. They may take a half hour to several hours at a specific plant, often leaving cars on the main line. This causes major blockages and delays to everything else wanting to run on the main line.
In the example shown, there are potentially many industries along this Twin Cities and Western line that intersects with BNSF, UP, and CP. In areas like this, especially if there is just a single track main, it may not be possible to pull the whole train off the main line to service the industries.
Typically, local freights are the slowest and have the lowest priority on the railroad. To help people appreciate what a local freight train actually does and the time required to make its moves, a graphic simulation will show on the slides.
This local freight will pick up cars A and B, put them next to car 8, and leave cars 7 and 6 on the spur.
Okay, first the train cuts off cars 8 and 9, leaving them on the main line, and you got to make sure to set some handbrakes on them to prevent them from rolling. The train moves forward, throws a switch so that it can access the spur. The trainman may need to get out of the train to unlock the gate to the industrial area.
The trainman backs up the train, couples up A and B, releases the handbrakes on A and B, and connects them to the air brakes on the train.
The train then moves back onto the main line. It then backs up, decouples cars A and B, couples them to 8 and 9, and sets the handbrake for cars 8, 9, and now including A and B.
Then the train pulls forward. Then the train backs up, drop-offs cars 7 and 6, sets the handbrakes for them, moves onto the main line, and locks the gate to the industrial area.
The trainman then throws the switch so the train can go backwards to connect to cars A and B, which are also connected to 8 and 9.
Finally, the train backs up to couple cars B and 5. The trainman then releases the handbrakes on A, B, 8, and 9 and connects the air brakes and tests them.
The trainman can finally move the train ahead on the main line. During this process, which may take 25 to 30 minutes, hopefully less, no other train can pass on the single-track main. The local freight is effectively parking on the main line. With this simple but typical scenario, you can see how important it is to consider the potential impacts of local freight movements when planning new infrastructure or services. As a point of contrast, industrial parks or ports with internal rail circulation provide opportunities for pickup and drop-off cars without impacting the main line.
The example shown is the Semo Port Railroad on the Mississippi River. Between the BNSF and UP main lines, the industrial complex includes a rail line connected to both mains and to the river port, with some ancillary tracks as well.
All right, well, thanks. And let's move on to tonnage trains. These are the second lowest priority in the railroad.
Tonnage trains typically carry oil, coal, grain, rock, etc. After local freights, tonnage trains are the second slowest type out there. They are simply powered to get over the maximum grade along the route.
Tonnage trains are also called bulk commodity freight trains and unit trains. Why is that?
Well, the trains are typically assembled at a single origin and disassembled at a single destination. The train is not broken up en route.
An unusual example of a tonnage train is the juice train in Florida. It carries frozen orange juice. Because of its high-value cargo, it keeps a tight schedule. It runs so fast that it can stay ahead of any Amtrak train.
The average speed for most tonnage trains is in the 20 to perhaps 30 miles an hour category. They are not powered for speed, just to get over the grades along the route.
What about braking on tonnage trains?
Typically, these trains are the most difficult of any train type to stop because the weight of the train is very high. We will explain braking systems later.
All right, thanks. Well, let's move on to manifest trains.
Manifest trains are the third lowest in priority. They have the most varied cargo, a mix of fully loaded cars and empties with multiple commodities, origins, and destinations. Therefore, their weight and braking distance will vary quite a lot.
Do these trains pick up cars on the main line?
No, they will typically pick up cars at local distribution yards, which may be separated by 50, 150 miles. And these groups of cars have been aggregated by local freight trains. Manifest trains typically travel at an average speed of 30 to 40 miles an hour, with a maximum being about 60. The time to brake depends on car loading. Cargo can be more variable than cargo for tonnage trains or local freights, so it can be more time-consuming. And because manifest trains only stop at distribution yards, they travel at somewhat higher average speeds.
Okay, so let's moving on to intermodal hotshots.
Intermodal hotshots are the fastest freight trains out there. They have top freight priority on the railroad.
And Dick, what makes these freight trains intermodal?
These trains connect with ships and trucks at major terminals or ports. The intermodal shipping containers are dimensioned to work on trains, trucks, and ships.
All right, as a way of describing the scope and scale of the intermodal freight traffic in the U.S. and therefore their characteristic movements, Jared, could you explain or describe this excerpt from the FRA National Rail Plan?
Sure. As you can see by the green columns, which represent the share of rail and freight transport, rail has the largest share of the transport market in the 500 to 1,500 mile range. In this mile range, the type of freight train used is predominantly the intermodal freight train that carries cargo of high economic value. These are commodities and other items that people want to get there fast. This map shows the main intermodal freight train routes connecting the top mega regions in the U.S. The major terminals at which they load can be thousands of miles apart.
So, Dick, how long do the intermodal trains get?
Well, the typical length of an intermodal train is over a mile, although they can be as long as 2 miles.
Wow. So does FRA regulate the length of the train?
No, but practical realities constrain the length. These include such things as the length of passing track, because sooner or later even the intermodals wind up on a passing track. Difficulties with repairs. The longer the train, the longer it can take to find a problem out on the line of road. Some municipalities have time limit ordinances for blocking of roadways. This can constrain train length also.
All right, so let's talk about speed and stopping frequency.
Intermodals only stop to change crews and add fuel. They average 50 miles an hour or more with a maximum authorized speed in the 60 to 75 mile an hour range.
Well, it's really hard to imagine breaking this extremely long train that travels at those speeds.
You are correct. We will go into braking systems later, but suffice it to say that all trains use conventional air brakes, which brake each car in sequence. Some intermodal trains are now using electro-pneumatic brakes, which can brake all cars simultaneously. Electro-pneumatic brakes can significantly reduce braking time. This does help in braking long trains.
All right, so in summary, you can see in this slide the different kinds of freight train types that we've talked about, their train length. You can see the increasing range in miles and also the increasing average speed in miles per hour. Let's move on to passenger trains. And let's start with commuter trains. Jared, would you go over the characteristics?
Sure. Commuter rail trains are usually 4 to 12 cars in length. They range in distance from 20 to 60 miles. The average speed is between 30 and 45 miles per hour, and the braking is typically conventional air brakes.
The average speed is not that great because typically the commuter train makes frequent stops, and the dwell times plus the time that it takes to slow down and start up just chew into the average speed.
The local commuter has a range of 20 to 60 miles. The example shown is the MBTA commuter train outside of Boston. A local commuter train makes every stop, which are typically 2 to 5 miles apart.
The Zone Express commuter train will cross multiple zones before stopping. The photo shows a metro train in Chicago, leaving Chicago Union Station. In this case, the first stop is Naperville, 28 miles out of town. Second stop is Route 59, a little further west. Then it goes to the yard. These are the only 2 passenger stops on this train.
For Zone Express, the average speed is 40 to 45 miles per hour and faster. Other Zone Express systems are New Jersey Transit, SEPTA, MBTA in Boston, and Metro North in New York City.
Local commuter trains typically run during a broader time frame, whereas Zone Expresses run during peak rush hour only.
All right, thanks. So now let's go on to the intercity passenger trains that connect 2 more metropolitan areas. We'll look at long haul, short haul, higher speed, and high speed.
The characteristics of long-haul intercity passenger trains are these. The length can vary from 10 to 16 cars, range anywhere from 800 to 2,000 miles. Speed is typically in the 50 to 60 mile an hour category, and they use blended braking.
Examples of long-haul intercity passenger trains are the Cardinal Amtrak, which is Chicago to Washington, D.C., 800 miles, takes about 24 hours. Amtrak Coast Starlight, which is Seattle to Los Angeles, 1,150 miles in about 35 hours. And Amtrak Southwest Chief, Los Angeles to Chicago, 2,000 miles in 40-plus hours.
The characteristics of short-haul intercity passenger trains are these. The length is more typically in the 5 to 8 car category. Range is 300 to 700 miles with stops every 10 to 50 miles, and it can vary widely. Speeds are averaging anywhere from 45 to 55, with a maximum at 79, although the Northeast Corridor maximum is 125. Where these trains typically cruise at these speeds. Braking, these trains are short, so brake propagation time is short. Brake propagation means the amount of time required for the brakes to apply to each car in sequence and is not very long. But at 79 or 120 miles an hour, trains like this can take 2 miles to stop. Blended braking is typical.
And examples of short-haul trains include the Amtrak Pacific Surfliner, San Diego to San Luis Obispo, 280 miles, about 8 hours. And Amtrak Cascades Corridor, Eugene, Oregon to Vancouver, British Columbia, 400 miles and about 12 hours. The Amtrak Northeast Corridor, Washington, D.C. to Boston, 450 miles in 8 hours.
The characteristics of higher speed intercity passenger trains are these. The length is typically 5 to 10 cars. Range is 200 to 700 miles. Average speeds are 60 to, say, 80, although, again, on the Northeast Corridor, 110 to 150 miles an hour max. And, again, they have blended braking.
Examples include Amtrak's Acela Express, which has a maximum speed of 150 miles per hour with upgrades planned for 220 miles per hour, and the Chicago to St. Louis Corridor, which is Class 6 track, with a maximum speed of 110 miles per hour.
The characteristics of high-speed intercity passenger trains are these. 10 to 12 cars, range 300 to 700 miles, average speed 100 to 130 with a maximum of 220 in the future. And these would have blended braking.
The image on the slide is of the California High-Speed Rail. As a point of reference, the authority recently issued a request for expressions of interest in vehicles, electrical multiple units, capable of operating at an average speed of 185 miles per hour.
All right, again, so this is a summary of the passenger rail, and again, we talked about commuter trains and the various types of intercity passenger trains. And as Jared and Dick talked about, the different train lengths goes from 4 to 12 up to 10 to 12. And you can see the range in miles and the average speed. All right, so in order to complete this vehicle picture, we've talked a little bit about it, but we need to have some understanding of the braking system. And there are 3 primary systems. Dick mentioned a couple. There's the conventional air brakes, the dynamic brakes, and the electro-pneumatic brakes. Jared, could you review these?
Sure. With a conventional air brake system, a compressor on the locomotive fills an air reservoir on each car. Air is pumped down the line to fill each reservoir, and when the brakes are applied, the air is released from the reservoirs to the brake cylinders.
This is a fail-safe system. If the air hose is punctured or broken, the system goes into emergency mode and the brakes apply immediately. You can see on this diagram, the locomotive is on the left. When the engineer applies the brake, he releases air from the brake line. A triple valve on each car detects this pressure reduction and then routes air from each reservoir on each car to the brake cylinder on that car.
All right, so let's go on to dynamic braking, which at the locomotive, the engineer reverses the traction motors to slow down the train.
Yes, the traction motors are essentially converted into generators. Reversing the traction motors takes the kinetic energy from the motion of the train and converts it into electricity. As the electricity is generated by reversing of the traction motors, the remaining kinetic energy becomes less. Therefore, the train slows down. Traction motors can slow the train down to approximately 12 to 15 miles an hour.
And Dick, would this analogy be right? Dynamic brakes are like downshifting into second gear when you're driving down a hill to slow the car instead of braking to save on the brake pads?
That is an appropriate analogy. With a diesel locomotive train, the generated electric power is dissipated as heat in brake grid resistors. The electric energy goes into the atmosphere. For an electrified train, the generated electric power can go back into the grid via the catenary. The word regenerative is used when power travels back into the supply grid.
And who uses dynamic brakes?
Most freight and passenger trains uses it. Amtrak uses dynamic braking on its electrified trains and diesel trains.
All right. Well, this slide says caution. Dick, what is the caution about dynamic braking?
Well, one of the things you have to keep in mind is with dynamic braking, the braking effort is concentrated in the locomotives, which are typically at the front of the train. The compression factor is huge going downhill, especially with sharp curves and light or empty cars right behind the locomotives. The empty cars are prone to crumple or pop off the rails. Dynamic brakes should be used carefully, depending on site conditions. They should be used in concert with conventional air brakes. Okay, this slide illustrates the compression or slack action from the cars to the locomotive. The total slack action on a freight train may be 30 to 40 feet. This means the locomotives could move 40 feet forward before the rear of the train even starts to move. Blended braking is used to reduce slack action, conventional air brake and dynamic brakes.
Is it difficult for the train personnel to manage two braking systems concurrently?
They certainly need to know what they are doing, and freight and passenger trains differ. In freight, the two systems are typically separate, and yes, it is more difficult to manage and coordinate two systems at the same time. In passenger, the two systems are together with one lever to control both braking systems. Together, they are called blended brakes.
Okay. Well, thanks. And so now we have the last type of braking, which is electropneumatic. And Jared, could you give us an introduction?
Electropneumatic brakes are a type of conventional air brake. Instead of applying the brakes to each car in sequence, one after another, the brakes are applied to all cars at the same time. Still, the lag time is 0 seconds. Dick, how does this work?
Through a separate electrical line that runs the length of the train, an electronic signal is transmitted simultaneously to every car. The signal causes the air to be released from each reservoir at the same time.
So, Dick, could you talk about the differences between braking for both the freight side and braking for passenger trains?
Okay, consider this for freight. Compare a loaded coal car weighing 130 tons with an empty coal car weighing 30 tons. The difference is a factor of 4. Freight trains have longer stopping distances than passenger trains because of their weight, their length, and the time it takes for the brake application to go down the train. The train personnel for a freight train must skillfully use braking to deal with circumstances that arise. For example, if a train is on a hill, the front of the train may be on the downgrade and the rear and needs braking, while the back of the train may still be climbing the hill.
All right, now let's look at the passenger side of things.
Compare the loaded passenger car and the empty car. The difference is less than 10%. Passenger trains are shorter and lighter, so braking is normally much easier.
Dick, apart from the passenger and freight distinction on braking distances due to their relative weights, does the power source, diesel or electric, make a difference in the stopping distance of a train?
Not really.
Okay, so, well, thanks. So after braking, I can imagine that getting the train back up and running takes some time. What's involved in that?
Well, the reservoirs on each car need to be refilled with air. The air is pumped back into the reservoir of each car in sequence. This does take time.
This process, which is the same for both conventional air brakes and electro-pneumatic brakes of pumping air down the train line, is described by these phrases: releasing the brakes, pumping the brakes off, and recharging the reservoirs.
There are occasions when the trainmen cannot pump air back into the system fast enough to keep the train moving. Ideally, however, a running release can be accomplished. This means the train might slow down from 60 to 40 or even to 20 while air is being pumped back into the reservoirs, but the train doesn't stop. It avoids the stop, which is good.
So here's a braking system summary. For conventional air brakes, when the brakes are applied, the air is released from the reservoirs. In dynamic brakes, at the locomotive, the engineer reverses the traction motors to slow down the train. And for electro-pneumatic brakes, instead of applying the brakes to each car in sequence, one after another, the brakes are applied to all cars at the same time.
And this is a braking system summary table by train types, and shows that all freights and all passenger trains use conventional air brakes. Some freights use dynamic brakes, and some intermodal and tonnage trains use the electro-pneumatic brakes. And looking at this table, it seems like the freight world is a little ahead of the passenger world in terms of braking technology. Why is that?
Well, you're basically correct because the weight they carry. The freight train owners have pushed to develop better braking technologies as the trains get heavier and longer.
All right, Dick. Well, let's sum up. How would you sum up what we've covered in this webinar so that it's most useful to the planners and engineers working on railroad projects?
As we are planning passenger services in existing freight corridors, we want to start with a better understanding of the characteristic speed, length, braking distance, and movements of each train type, and then begin to understand the cascading impacts of each train type on train traffic within the corridor.
Well, thanks, Dick. So this has been great. And in our next webinar, we'll put the train performance characteristics in a context and look at the track configuration tactics and the characteristics of single, double, triple, and quad-track railroads.
And we will stress how important it is to get all parties around the table to get agreement on the plans and sign off on the plans.
Well, that's all for now. Thank you to Dick Cogswell, Jared Filipkowski, and all of you in the audience. And to see this webinar again, visit FRA's Web Rail Network Development Oversight Guidance at fra.dot.gov. Have a good rest of the day.